All right, so this is the first of several lessons introducing the ideas of graph theory, which is a field of geometry that you're probably unfamiliar with. And so a lot of this is just understanding some notation and some vocabulary here. So in graph theory, we look at graphs like this, not bar graphs or line graphs or scatter plots, graphs that show paths between different points, vertices and edges we call them. And a graph like this we can describe by its order and its size. The order is represented by the number of vertices. So in this case, this graph has 1, 2, 3, 4, 5, 6 vertices, and so it has an order of 6. And the size is represented by the number of edges, these lines we see here. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have a size of 9 and order of 6. So order is 6 and the size is 9. And those phrases we see a lot. And again, so much of this lesson is getting introduced to a number of terms. All right, the degree of a vertice is a measure of how many edges connect or adjacent to that vertice. So if I look at vertice F, and I zoom in here, I can see there are 1, 2, 3 edges that connect to it. So we say that F has a degree of 3. So the degree of F is 3. We talk about adjacency, edges that are adjacent to another edge. It's how many edges are connected to it in some place. So again, erase all my little marks here. So AD is this side right here. So any other edge that connects to either A or D, we say is adjacent to AD. So let's look at point A. I have this side here is adjacent to it, and this side here is adjacent to it. So there's 2 sides adjacent to A, but there's also vertice D. And if I look here, I have this side is adjacent to D, this side is adjacent to D, this edge is adjacent to D, this edge is adjacent to D. So 2 that are adjacent to A, 4 that are adjacent to D. So altogether, how many edges are adjacent to AD? Some crazy math here, 2 plus 4 equals 6. All right, and so this graph shown we say is not planar, which a planar graph is one in which there's no edges overlapping one another. And sometimes there's no way of avoiding it, but sometimes there is. And in this case, we can adjust the way this graph looks so that there's no edges overlapping, intersecting any others. And in general, that's preferable. It makes it easier to understand and follow paths if we have them or minimize the number of intersections. And so there is a way to make this graph a planar graph. And how can we do that? Well, if I move this B over here somewhere, and same thing with E, move this over here, I'll still have the same connections, all the same edges, all the same vertices, but they won't overlap at all. So let me show it to you like this. I'm going to take B and move it right here. Which means these 2 edges here would now look like this. And I'll do my best to erase the old B. Goodbye, old B. All right, and then do the same thing for E. I'll move it over here somewhere. And one key idea of graphing is that it doesn't really matter the position of things. It doesn't matter how long we draw the lines. It just matters how they relate to one another. And so if I imagine E over there, then these 2 edges will look like this. And so if I erase what we used to have, you can see that now we have what we call an equivalent graph. This graph is equivalent to what I started with, but notice none of the edges are intersecting or overlapping one another. But it is equivalent. It just tends to be a little easier to visualize or to read. All right, graphs don't have to have straight edges. And so here is a graph that has all the edges are curves, which again, there's no rule saying they have to be straight lines. So first I want to ask, is this considered a simple graph? Well, what's the definition of a simple graph? A simple graph is any graph in which there's no multiple edges connecting vertices. And also there's no loops. So for example, when I say a multiple edges connecting vertices, let's look between A and B. Between A and B, there's this vertice here, and that's it. There is no, this edge. There's an edge from A to B right here, and there are no other edges connecting A to B directly. But that's it, there could be. I mean, if I adjust the graph, now there's 2 different edges connecting A to B. Oh, look, now there's 3. Now there's 4. So what I'm now doing, this would now make it what we call a multi-graph. However, none of this was actually here. And if you look at the whole graph, there are no places where you see 2 edges connecting the same 2 vertices. At most, there's one edge connecting any pair of vertices. Plus, there's no loops. A loop is where you would have something potentially that goes like this. It starts and ends at the same point, but there's none of those. So in the end, is this considered a simple graph? By the definition of a simple graph, yes, this is. So yes, because there are no loops or edges or multiple edges between the same 2 vertices. All right. So just before I go on, don't think simple means it must be an easy question, just it's the definition of a simple versus a multi-graph. Okay, that's part 1. The second part is how many more edges must be added to make it complete. So what's a complete graph? A complete graph is one in which it's a simple graph, so there's no loops, no multiple edges, but as well, every single vertice has one connection, one edge to every other vertice. And so if something is a complete graph, again, it still must be simple, so no loops, nothing like that. But there also must be a way to go directly from each vertice to another, to every single one. And there's a lot here, but for example, if I look at A to D, there's no way right now to go directly from A to D. I can go from A to E, and then from E to D, but I can't go from A to D directly. So this is why we say this is not a complete graph. But if I add one, and I'll continue to draw a curve. There, now I can go from A to D directly. Are there any others? And there's one other that from E to C. If you look at E to C, there is no way to get there directly with one edge. But now there is. So this now is considered a complete graph. It's still a simple graph. There's no multiple edges between the same 2 vertices, but I can now go directly from every vertice to another one with a single path, a single edge. All right, lastly, focusing on complete graphs. Well, complete graphs, we denote with a K and a subscript. The subscript is the size of the graph, or the number of vertices. So one idea is that if we have a complete graph, there's a fairly nice relationship between the number of edges and the number of vertices, or its size. And that relationship is this. That's the number of edges, also known as the size, is always the same as n times n minus 1 over 2. N being the number of vertices, the order. All right, so for this question, we have 3 different complete graphs. So this has 9 vertices, this has 10, this has 11. And each one of these, imagine you have all these points, and it's a complete graph, so there's a direct line connecting every single one to every single other one. I'm far too impatient to actually try drawing all that. There'll be a lot. So first, let's figure out how many edges that would be. So for a complete graph with 9 vertices, so K9, the number of edges would be 9 times 8, n minus 1 divided by 2, which is 36. If we have 10 vertices, the total number of edges, the size of it, is 10 times 1 less, 9 divided by 2, so 45. And then same thing for if we have a size of 11 or 11 edges. 11 times 10 divided by 2. So this graph has 36 edges, this has 45, this has 55. So the idea for this question is, well, what if we combined all these edges to make some new super graph, some new complete graph? What would be the order of that? What would be the number of vertices? What is n, basically? So what I want to do first is add all these up, which pretty quickly, I add all this up, and I get 136 total edges. All right, so now we need to think what complete graph, of what order, or how many vertices, same idea, would have, of our complete graph, would have a total of exactly 136 edges. Well, I can now use that same equation I see at the top of the screen, but solve for it. So I know that in this case, n times n minus 1 divided by 2 must equal 136, and solve for n. A lot of ways I can do this. Multiply both sides by 2 first. I get 272 on one side, and if I distribute the n, I get n squared minus n. I have the makings of a quadratic equation. I could try factoring this, although it's a little bit annoying to think of two numbers that multiply to negative 272, yet add to negative 1. I can also just solve this by graphing and find the x-intercepts. So if you solve this any way you want, we just want to be pretty quick with it. Personally, I would just solve by graphing because it's easy to type in. And you should get two x-intercepts, one at negative 16, one at positive 17. That said, an order of negative 16 doesn't make sense. The smallest order you can have is 1. An order of 1 is a single dot, right? You can have that, but you can't have an order of less than 1. And so that said, that there I don't need to worry about or think about. It's the 17 that matters. And so I can say, therefore, must have an order of 17. Keep in mind, this formula here is not in your data booklet, so it's not a terribly complex formula, but it is one we'd be helpful to be familiar with. Going forwards, there'll be a lot more to learn, but before we can learn more, we want to be really confident and secure with what all these terms mentioned today. Not mixing up order and edge and all those sort of things that I will probably do as I talk in future videos. So I apologize in advance.